Welcome everyone to Iron a show where we look how Tribetal looks like from the inside, how you can build an awesome, modern, distributed, highly reliable, very fast database in Zeek without using any kind of dynamic memory allocation, using like 100 asserts per function and all the other cool stuff. Okay, so let's jump straight in this time. What we are talking about? Well, we'll more or less continue our last episode where we were discussing a FreeSet. Okay, let's. I'm in the mood for just jumping straight in the code today. Okay, so we have our FreeSet. What is a FreeSet? A FreeSet is essentially a memory allocator, except that it doesn't allocate random access memory RAM. It allocates memory on disk. As a reminder, the disk in Tribetal is split inside equally sized blocks called blocks. Each block is half a megabyte long. So the task of a FreeSet is just to give you free blocks when you need them, and also to maintain the metadata to mark blocks as free when you are no longer you are no longer in need of those. So because blocks are fixed sized, the metadata maintained by the FreeSet is super simple. It is just a bit set of allocated blocks. So when you want to get a free block, well, you just find the first unset bit here and return it. There are, and conversely, when you want to mark previously allocated block as free, you flip the bit in the blocks back. But there is one twist here. The twist here is that at any point a replica might crash, and when replica crashes, it restarts from a checkpoint. So what might be the case is that you started from a checkpoint, you appended some prepares to your write-ahead log, you executed some prepares, you created some new data structures in the grid, but you haven't yet updated your superblock. So when you crash and restart, you restart from that same previous checkpoint, and you retrace the steps that you've made so far. And herein lies the problem. If during those steps you mark some grid block as freed and then allocated a new block, and that freshly allocated block turned out to be the block that you just freed, then you won't be able to restart from this checkpoint later, because later when you use that old block it would be overridden. So that is the twist. When you free blocks, you might actually you have to defer your deallocation. Deallocation has to happen when you wrap over to the next checkpoint. So yes, and this is this process of wrapping up to the next checkpoint is exactly what we are going to be talking today. But before that, let's recap other bits and pieces from the previous episode. So one thing is that there is also the index. The primitive operation which FreeSet supports is find the first unset bit. And because the strategy for allocation is that we always try to allocate the earliest free block, so that we don't fragment our disk and try to keep our grid compact. So if you imagine how typical grid looks like in memory, it is has gigabytes, maybe terabytes of allocated blocks, and then some small fragmented subset where there are free blocks. So if you're going to try to find first free block in this situation, well, you have to go through the entire terabyte of allocated bits. And again, this is not comparatively, this is not that much data because we use only a single bit for an entire grid block, but still it's a lot. So that's why we have an index. So for every, I think, 256 bits in the actual bit set, we store 1 bit in the index, which is set if every bit in this 256 bit lane is set. That way to identify the first unset bit, you actually first do this in the index, which is 256 times faster, and then you do this in the blocks. Okay, and the final thing from the recap, which would actually be a nice segue into what we are talking about today, is that how exactly do you store bit set in the grid? So what we are looking, and this is kind of important meta thing about trackability. Most data structures exist in two variants. There is what you store on a hard drive, and then there is what you store in memory. So right now, on the screen, we are looking at the FreeSet, how it looks in memory. When we store it on disk, we actually store it in a slightly different way, because this data structure optimizes for random access. This is just a bit set. For disk, we actually want to optimize storage. We want to use less bytes for a FreeSet. And to do this, we use the so-called EWAR encoding, which is super simple. This is essentially a run length encoding for a bit set. So you take your bit set, then you slice it up into the words of 64 bits. So just longs or whatever, U64. Then you look at those words and you note all the words which are either all ones or on zero. So there's three kinds of words. There is a mixed word which contains zeros and ones. Then there is a word which is just all ones, so 2 to the 64 minus 1. And then there is just zero word. And then for mixed words, you encode as is. But for uniform words, instead of like encoding them as is, you say, okay, the next like 100 words are going to be uniform ones. This feels like a very stupid encoding, which should not compress like basically anything, because like what is the probability that like in a random bit set like you get like 64 bits in a row to be the same? But the thing is, for our FreeSet, the bit set is very much not random, because we allocate the earliest free block first. We actually get exactly the situation where we have a lot of bits set as 1, then we have like some amount of non-uniform words, and the tail is all bits set to 0. So, okay, now, how exactly do we store those compressed encoded bit set on disk? The general mechanism for that is the so-called trailer, which is, yeah, well, it is kind of a trailer. So basic idea is this: we store data as a linked list of blocks, where each block contains an address and a pointer to like the next block in the linked list. And then in the super block, we include just the address of the first block in this linked list. So let's look at this checkpoint trailer data structure. It is generic because actually not only like there is a bunch of things we encode in this way, not only the FreeSet, but the FreeSet was actually, I think, the first data structure that got this treatment. Okay, so that should be relatively straightforward. Okay, what we have here? We have obviously the grid, because, well, this is a linked list of blocks, so we gotta read blocks. Then we have the type, which I think is just like, you know, a tag of what is this? Yeah, okay, so we actually store 2 data structures. In this way, we store FreeSet and client sessions, and client sessions is something which we are yet to cover. Okay. Then we have next tick, which I'm not sure I've covered, but, well, this is going to be a nice excuse to cover it once we get to its usage. Then we have like read and write, because obviously we want to be able to read this data structure from the grid. We want to be able to write this data structure from the grid. And again, like this is something I repeat again and again, because Target doesn't allocate memory dynamically. That means that all concurrency has to be bounded. Like whenever like you do anything concurrent, you gotta store some piece of data which stores the state for this concurrent operation. And that means that all concurrency, all that is happening, is actually reified as specific concrete data structures. And looking at these 2 fields, you realize that, hey, this thing is going to read blocks one by one, because we only have a single write and a single read. If this thing supported parallel reading, we would see something like, okay, we have like an array of like 16 reads, but because there's just one, we know, hey, there is like 1 read, 1 write, but potentially those 2 can happen in parallel because there are 2 of them. But I think actually it's like not really possible right now that those are concurrent. Okay. This is okay. This is interesting. So we are going to use a bunch of blocks for our linked lists. And here we store like all the blocks. So this is like their addresses, their checksums. I guess this is the blocks themselves. And for block bodies, like right now, I actually don't understand what's the meaning of this field. And then we have something some fields for like double checking and insertion. We have the size which we expect the thing to have, which we typically know upfront, and then we like separately maintain like the total amount of bytes read or written, just so that we can compare those two and make sure that we didn't miss anything. Okay, so let's continue reading it. Initialization. As usual, initialization accepts allocator, and this allocator allocates memory dynamically, no problem. But after init, there is no allocator, so all the memory which we might use has to be allocated here. Okay, so buffer size is presumably the maximum size of the data structure we can encode into checkpoint trailer. It looks like something is burning outside, but hopefully this is not related to the place where I live. Okay, then what is a chunk size? Okay, yeah, so like conceptually, checkpoint trailer stores like a slice of bytes, but it might need to slice this slice up into smaller chunks, because blocks are only half a meg in size. So if you want to store like 10 megabytes in your trailer, then you'll have to use 20 blocks. So this is like the chunk size is the size which fits into a single block, and it should be like constant block size. Oh, right. We don't have block. We have message body size, but we don't have block body size, and that's why we introduce chunk here. Or probably, yeah, we should just introduce this as a global concept. Anyway, so that's just the size of block minus the size of the header, because as usual, reminder, one pattern we use in TargetBittle is that we try to really squeeze everything out of every specific data structure. So we like try to use anything we wrote like everywhere. So not to create more entities, and that is why we use the same header data structure both for our network messages and for our blocks. And in particular, a block is a valid network message. So in the repair protocol, when a replica wants to repair a missing block from a grid, it asks for a block literally. And the other replica just like reads this block and sends it as is over the network. There isn't any need to add some kind of an envelope around that, because the header is already there, which allows you to like simplify the code and to avoid like extra memory copies. Okay, so coming back to init. Okay, so we have like this is a maximum size of a trailer. We divide it by the chunk size max. That's like the amount of blocks that we will need. We allocate the array of blocks, allocate memory for each of the block. Then we allocate block borders. And yeah, this is kind of... Okay, yeah, I don't... Okay, it kind of like feels that like these block bodies are going to be pointers inside these blocks just to simplify. Okay, yeah, I think I got it. I think those block bodies are going to be pointers inside those blocks, and the reason why we need separate pointers rather than just recent blocks is that because, well, some blocks might be only partially full. So you need to like store this information, and we might as well store it separately. Okay, we have like block addresses, block checksums. Okay, we are done. I guess the interesting part here is open and checkpoint. Yeah, so open is the read path. and checkpoint is right. I guess let's actually start with a checkpoint, like, because to understand like how to read the data, we need to understand the format of the data, and for that it's actually simpler to start with the right path. Okay. So what do we do here? Where is actually, okay, trailer decode chunks. What does it do? Trailer. Aha, okay. I got it. So decode chunks. Yeah, okay, so it seems like by the time the caller calls the checkpoint, we already should have the data stored inside those block bodies. So like I was like looking at this function, I was thinking about, okay, so where is the data we actually store here? But it seems like the contract is that the caller like manually encodes the data inside inside the blocks, inside like the blocks we're already storing. So the first thing we do here is that we compute the checksum of the entire thing we are going to store, which is like technically not needed, because remember, blocks have checksum, and because there is a linked list, the checksum of the root block like already transitively, indirectly, but protects with the checksum the entire thing. But computing the checksum for the entire thing is still helpful to make sure that there are no programming errors. Like, for example, if you, for some reason, accidentally cut this linked list in the middle, this checksum for the entire thing will help you out. Okay, so okay, yeah. So how does it work? We look at the size, and okay, size is again something which the caller sets for us. We look at the size of the data, we divide it by the chunk size, and that's going to be like the number of our chunk counts. Then we say that, okay, the corresponding block body, as I said, is the slice of the block. So it starts where the header ends, and its size is the chunk size. And the size is either like the entire size of the blocks for every chunk except the last one. And for the last one, it's going to be just like whatever is said there, which is relatively simple. So, okay. We check if we are the last block, and if we are the last block, then our size is the total size of the trailer minus the size of the previous blocks. Otherwise, it's just like the maximum size we get in a chunk. Okay, so this is like basically, okay, so yeah, now it makes sense. So like this entire thing is just like to make the actual source code simple. Because the thing here is that we get our entire trailer as a slice of slices. This is not like some kind of like abstract iterator or stream or whatever, it's just like slice of slices. So we go and we call those slices like small slices chunks. So, okay, yeah, now it makes total sense. We have some data. We chunk it, and each chunk we fed to our checksum thingy, and then compute the checksum. And say, okay, so this, we have like, so file transferred 0 bytes. Now, this is interesting. Like, you know, when you do functional programming, there is like this idea that like, that you always like normalize things. That, for example, you don't make a distinction between vector which is empty and like optional vector which is sum of an empty vector or none. Or similarly, like, you know, you don't treat like optional string and an empty string as separate. Like you always see like a neutral operation, and like kind of like you don't like. And the idea here is that you shouldn't treat size 0 as separately. But when it comes down to doing this KO, this actually is a meaningful distinction. Like there is a difference between not doing a right syscall and doing a right syscall of length 0, because, well, syscall is asynchronous, syscall is slow. So that's why in this like low-level disk access code, you actually do see those 0 sizes, special cases. So, okay, if we actually have to encode something, if the size is greater than 0, then, well, we need some blocks to store this. Let's use what we've learned last time and use FreeSet to allocate the blocks. As a reminder, FreeSet doesn't allocate blocks directly. Rather, first you reserve like the upper bound of blocks you might allocate, and then you use that reservation to actually allocate the block. And you don't have to use all the reservation. You might like allocate only half of the blocks from what you reserved, and then you return the blocks back. The reason for that is that we want to support concurrency. We'll probably talk about this more when we get to compaction, but the idea here is that you could like the idea is that if you have like some concurrent processes, what happens is that like let's say like 4 things want to concurrently allocate blocks on the grid, and they have to do this deterministically because we want to guarantee that the grid is fully deterministic. What they do is that they sequentially make their reservations, which enforces determinism. And then in parallel, using those reservations, they actually allocate blocks in arbitrary order, which might not make a lot of sense to you, but this is important. So I guess if this is confusing, please rewatch the previous episode and wait for compaction, where it becomes crystal clear why we do this. Because here there isn't actually any concurrency. So here we don't actually need this reservation infrastructure. Anyway, we want to allocate grid blocks. We go and reserve the required amount of blocks, and well, the required amount of blocks is the size of a trailer divided by the size of a single chunk. After that, we forfeit this reservation, and we double check that we actually used up reservation fully, because a reservation supports this use case of like not using the entirety of it. But in this case, for FreeSet, we actually exactly know the amount of blocks we need. So in the end, we can just assert it. Okay, and then for each of the blocks we want to reserve, we actually acquire this block, we allocate it, and store in our address, and mark checksum as undefined. So this block addresses is where we should be storing these are the actual blocks where we be writing our data. An interesting digression. You see that what we are doing here with like block checksums and block addresses is essentially like open-coded, well, it is like open-coded array list and open-coded structs of array. So although this is a slice, you are actually allowed to use only this amount of data from it. And like, you know, technically in Zeek there is like, how is it called? STD array list. unmanaged. Yeah. So technically, this is std array list unmanaged. And because we have two of them, and they are actually in parallel, I think this is actually like the multi-array list thingy. So something like this, struct address use64 checksum. Yeah, and the question is like, why we are not using this thing, and the answer is that it's kind of like, you know, just simpler to open code it. Like I don't think we've ever had any bugs with, like, you know, just using slices and manually slicing by length. So kind of like it's just simpler. But again, it's like not a strong yeah, you only has to do this one way. If like in some cases like multi-array list becomes easier, then why not? You could use it. Okay. So we've acquired the blocks. If we actually need to acquire them, and then actually interesting. I bet that FreeSet reserve actually checks that the count is greater than 0. Okay, yeah. Okay, there is this check. That's why we have like this if here, and that's like, and like the underlying reason why we cannot make this just like a no op, because when you talk to disk, you actually do want to avoid zero-sized disk writes. Okay. So now we need to start process of writing disk, and here, if you recall, I kind of like glanced over next tick. So now we need to, there's a good opportunity to cover it. Okay, so suppose that the trailer size is 0, and we realize that here actually like we don't have to write anything to disk, like we are done here. What should we do? Well, we should invoke this callback, and one might think that like, okay, let's just invoke it right here. Like why not? Like why do we need this next tick machinery? And this is actually 90 pattern. This is like in the asynchronous programming, there is this guideline that every function either needs to be always asynchronous or always synchronous. So if you are accepting callback, then either every time a function is called, by the time a function has returned the callback, should get executed, or it never should be the case that it is executed. So it's like always or never. And in kind of like in this branch, we are going to hit the later case. We are not going to execute the callback here. It will be executed later. So we must arrange it in this branch to invoke callback later. And this is essentially what nextTick machinery is doing. It adds this callback to a linked list of callbacks to be invoked after the current iteration of event loop. So why do you need it? And there's like two reasons. Like one like very specific and one more philosophical. The specific reason is that if you don't do this, you might end up hitting a stack overflow, where if you get a series of callbacks which are invoked one after another, you actually like get like a lot of stuff on a stack. So kind of like, you know, if you look here, so if we invoke the callback right here, then at the time that we invoke it, like all this stuff is still on the stack. And if we invoke it on the next iteration of event loop, well then there isn't going to be anything above this callback on the stack trace. The second reason, like more philosophical, why you don't want to invoke the callback immediately is that it will hit re-entrancy. So you know, we are still in the middle of this function. Like for example, we have like this defer here. And if you invoke this immediately, then you'll actually be executing some code while this function hasn't exited and hasn't properly established all the invariants. So it might uncover some logical bugs. Okay, there is a question. I kind of lost the context for this checkpointing. Is this checkpointing just a grid FreeSet of the entire database state? Does a superblock write accompany this checkpoint? Okay, this is a great question, because yeah, it's kind of like that is the trouble with like this LSM stuff. It has like a lot of moving parts, and I'm trying to like slowly build a big picture, but yeah, it's easy to get lost. So let's start like this. What is even the state of a database? I mean, the disk state. And the answer is that that state is the superblock. So the superblock like contains like the root pointer to everything else on disk, because everything else is essentially like a bunch of persistent linked list. And the checkpointing, like abstractly, means that we prepare a new superblock in memory and then we write it to disk. So this is essentially like atomically swapping the root of our data structure. Then we need to think about like what data structures are actually like stored, like, well, not stored in the superblock, but are referred to by the superblock. And one of those data structures is the FreeSet, the list of free blocks. So if you think about it, what you store in your database is not only like, you know, the actual data, the actual tables, but some metadata about what areas of the grid are free, what areas can be used for further allocation. So this is what FreeSet is. And that means that when we get to the point where we need to checkpoint, where we need to swap our superblock, we need to encode the currently allocated blocks into the data which we include in the new superblock. Answering the question more directly, yes, checkpointing checkpoints the entirety of a database state. Right now, we are looking at one particular aspect of that database state, namely the list of free blocks. And I would say that checkpoint is a write of a superblock. So checkpoint happens once the superblock data hits the disk. Hopefully this answers the question. Okay, yeah, so basically that's what we are doing here. Here we invoke a callback, but just on an empty stack. And if we look on this like actual callback that we invoke on the next stick, that's well, that's checkpoint done, and the checkpoint done makes sure that the total amount of I/O is equal to like the size of the trailer we're expected to see, and then it calls the callback. Okay. By the way, another interesting pattern. So how do we store this callback? We store like the callback is actually an enum, and it like tells you which concurrent operation is currently ongoing with a checkpoint trailer. So none means that like checkpoint trailer is idle. Open means that we are reading the data from grid, and checkpoint means that we are writing the data to the grid. Well, actually, yeah, okay. This is continuing to answer your question. This is important. So again, what we are writing here in this checkpoint are grid blocks. So we are allocating fresh grid blocks, and we are writing our data into them. So this is not actually the superblock. This is the grid. But as a result of this checkpoint, okay, actually, do we have some method here? Okay, yeah. Like after we read this thing, we get so-called superblock trailer reference, which is essentially the address and the checksum of like the head of our linked list of grid blocks that we have just written to the grid. And this superblock trailer reference is what gets actually encoded into the superblock. So let's FreeSet. So let's take a look here. As a reminder, we have superblock here. So this is like the superblock, like the actual bytes which are stored in multiple copies in the superblock zone of the data file. Inside the superblock, we store the SAR state. Inside of this SAR state, we store checkpoint state. And inside checkpoint state, we store this FreeSet last block checksum and FreeSet last block address somewhere. FreeSet last block address. FreeSet last block address. It should be somewhere here. Okay, yeah. FreeSet last block address. And those checksum and address is exactly the checksum and address we get here. So hopefully this gets a little bit more context about this checkpoint. Okay, so I think we kind of covered this like easy case where we don't have anything to write. We basically immediately invoke the callback. Now, what if we actually like have to write something? Again, like essentially, like what conceptually we are doing here is that a sync while loop, but because Zig doesn't have async, we are going to code this loop manually using essentially like a recursion callbacks. Okay, but at the same time, it's actually, you know, it's like simple code. Okay, so we checkpoint write next. We want to write next checkpoint block. First, we assert that, hey, we are in the process of writing the checkpoint. So what I was talking about, callback is an enum which says which concurrent operation is in progress. We assert that indeed we are writing something which is greater than 0. We assert that we haven't written everything. So block index is the index of the block we are currently writing. And we double check that if we haven't written anything so far, then we are about to write the first block. Figure out how many bytes we need to write. Again, for all the blocks except the last one, it's just like the entirety of the block minus header. And the last one might be slightly shorter. We get the corresponding block. We fill the metadata in the block. So again, block starts with a header. The header has some bytes which have different semantics for different blocks. Those bytes are called metadata. For trailers, this is trailer node metadata, which is the linked list, like the address and the checksum of previous blocks. So if we are writing the first block, then obviously we don't have previous blocks, so we just null it. Otherwise, we well, go and fill in the address and the checksum of the previous block. Then we, okay, yes, this is metadata as value. Then we actually go and write the header of this block. So we fill the cluster, we fill the metadata, we fill the address of the block itself. Again, like block, each block stores its own address so that we can detect misdirected write. We set the snapshot, and snapshot is something which is not completely implemented, so I'm not going to cover this. Then we set the size of a block. Again, this is chunk size plus the header size. We mark this as a block because, again, header are shared with all these are consensus messages. So block is just one message. And then we set the block type. Then we say, okay, now we have actually transferred this amount of bytes. we set the checksum, we set the checksum of the header itself, do some sanity checking that the data so far makes sense. We set the checksums. We mark block bodies is undefined. Well, yeah, because we've already copied this data. Well, where is mem copy? Well, actually, well, yeah, there is no mem copy here because this block bodies actually points inside our block, and we probably should do an assertion here that this is actually true. But okay, anyway, after this. Oh, yeah, this is a comment explaining why you actually must do this, because when we, as a reminder, like block pointer is block pointer is a pointer to a block. So when you ask the grid to write the block, it actually not only writes the data you passed it in, but actually like puts that exact block in the cache, and instead gives you some free block. So after this point, like the actual block stored here is going to be different, because you see, like this is actually like a pointer. Like we take a pointer to this element. This is super confusing, but well, that's the API we currently use. Okay, so yeah, we ask a grid to create this block, and when the block is created, we increment our block index, and if we haven't reached the end, we go and go to the next iteration of the loop, call the checkpoint right again. Otherwise, we are done. We say, okay, so we are done, and let's like call the callback. So that's basically it. We just have data, we write it to grid in very simple, straightforward pattern, and that's it. So, kind of like unwinding the stack. This was a generic trailer. So a generic like linked list which you can use to store some data on disk. Now let's look at how we actually use that to store the FreeSet, because that is going to be tricky. And this is going to be tricky for exactly this reason. You know, when you store a trailer in the grid, you need some blocks. So you go to the FreeSet and you say, hey, FreeSet, please allocate me, give me some data here. But you know, like, I mean, if you use checkpoint trailer to store a FreeSet, then like what is happening? Like is like other blocks which are going to be used to store the FreeSet free or allocated? What is happening here? This is like basically like Russell's paradox. Like if a barber who like shaves everyone. Well, anyway, I'm getting too carried away. So let's reduce the amount of confusion and actually go and look at how this works. And so I realized that I haven't, like, you know, haven't shown you like the entry point to the checkpoint, like what actually drives this whole checkpoint infrastructure. And well, we'll get to there, but for now, like, you know, think about this abstractly. So at some point we realized that here actually like we need a new super block. So we need to compute all information we need to include in the super block. In particular, like we need to like include, encode the FreeSet and put the pointer to the beginning of the linked list to the super block. Okay, so now this is going to be tricky, and I might get confused here. Okay, so we want to do a checkpoint. First, we do this include staging things, where we take all the blocks which are released, and we go and now mark them as free, because, well, this is a checkpoint, and at checkpoint, well, it actually becomes safe to treat all blocks allocated in the current checkpoint as free. But you're actually going to, you know, we're going to do this only temporarily. and then we are going to flip it back. Why is that? Well, because we'll still need to allocate some more blocks for that FreeSet itself, and to store the trailer. And we cannot use the blocks which are released, which are to be free in the next checkpoint, because we are not in the next checkpoint yet. Like we are right at the boundary between checkpoints, but we are at the old one still. So that is the thing. So we kind of like temporarily include release blocks. Then we encode our FreeSet, and like this encode means that we like do this EWA compression thing. So what do we store? And this is also like a streaming API. So okay, we get kind of like, you know, a thing which is going to feed us chunks of encoded data. Then we go to our checkpoint trailer. So FreeSet checkpoint is the checkpoint trailer, what we've been looking at the beginning of today. Those chunks are like exactly like pointers inside block bodies. So something we've seen before. And we go, and for each chunk in our FreeSet trailer, we ask our encoder to encode data in this chunk. So this thing is going to write this EWAR encoded FreeSet into this target chunk. And we add the total result to our like total size. Okay, so after this block is executed, we store in memory inside the checkpoint trailer data structure the encoded FreeSet, and that FreeSet, and the encoded FreeSet doesn't distinguish between released and free blocks. Because it kind of like includes all the release blocks in free. But at this point, we still have this separation between released and free blocks, because we actually like only temporarily edit them, and then we flip things back. I realized that I should probably show this more explicitly. So again, we have like the staging, those are release blocks, and then we have blocks, which are, I think, allocated blocks. So to include staging, we like union those two bit sets, and to exclude, we again do this the same. Okay. So now we go to our checkpoint trailer and call this checkpoint function, which we have just looked at. So this thing is going to write this data to a linked list of blocks on the grid. Now there should be some interesting where do you okay, yeah, this is like where the magic happens. So after we wrote FreeSet blocks to disk, and after we do like other things which grid need to do during checkpoint, which we'll cover later, we are going to call the FreeSet checkpoint method, and we are passing this list of block addresses which hold the FreeSet itself. And what this thing will do is that this will actually like do this like double buffering flip, where we say, hey, like all the release blocks are now free. So here we did this only temporarily. We kind of like pretended that released blocks are now free. Once we get to the end of the checkpoint in process, here we'll actually do this for real. And after, there is like this fun thing. So there's like, normal blocks which are like free or allocated or released, and then there are like blocks which store the FreeSet itself, which we have just allocated. And like the fun thing is that, well, we've allocated it right at the end of the previous checkpoint. But in the new checkpoint, these blocks are actually released because we no longer need them. So we essentially like allocated and immediately freed those blocks. So the state we expect us to see after is that the only released blocks are the blocks of a FreeSet trailer themselves, which is what we asserted here. We assert that the count of release block is exactly equal to the number of blocks we needed to encode the FreeSet. So now let's look at this like actual process where we like do this flip. So we go and we unmark each of the staging, also known as release blocks, and we mark the corresponding block as free. And again, if this block is free, then the corresponding index also needs to be marked as free. And then we go and mark the blocks which store the FreeSet itself as released, because well, we are actually no longer needing those. And I think that's it. So, well, I guess we'll take a little look at the overall flow of a checkpoint. I think this happens in replica. So read checkpoint. Okay, so replica drives checkpoint. Replica calls greet checkpoint, which triggers this hey, let's write FreeSet to disk procedure. And after that, where do we do? Okay, yeah, then like so we checkpoint agreed, then we like checkpoint something else. And okay, this is like where I guess like the answer to Brian's question is actually in like the source code. So after like that FreeSet checkpointing process done, and all the other checkpointing processes are done because well, we actually like more data structures that we need to preserve in Superblock. We actually go and say, okay, now let's actually write a new Superblock, and we go. And as part of like the data to the Superblock, we actually pass this FreeSet checkpoint reference. We pass the address of the head of the linked list. We pass the checksum, and we the checksum of the head of the linked list, so the checksum of a single block, and then we pass the checksum and the size for the entire trailer just to double check. And if you look at this checkpoint, what it will do is that it will set this to the actual data in the SR set, and then call that acquire function, which we already covered. Although I think we've only covered the read path of the acquire function. I don't think we've covered like the write path, but well, that's for some of the future episodes. But basically the idea after we do all that, we actually store the pointer to the beginning of the linked list of the blocks which store FreeSet to the superblock. Okay, I think that's it. This probably was one of more mind-scratching episodes where we really took a deep dive into some particular very narrow aspect of implementation rather than drawing pretty pictures. But well, there are these kinds of episodes as well. Okay. Interesting question, slightly related, but still very interesting question in chat. That target style mentions that there are differences between control plane and data plane, but what exactly are those differences? I think one of those differences is verification. We have this compile time parameter verify, which includes extra verification, enables extra verification in the binary. And on that compile time parameter, there is a command explaining our approach to the verification, specifically to the trade-off between performance and verification. And this is a great example of differences between control plane and the data plane. So let me try to quickly recap what this command talks about. So what is the problem we are trying to solve? The problem is that verification is in general costly. There's two competing goals. On the one hand, we want to be super correct. We want to run as many assertions as possible. We want to check everything. But on the other hand, we want to be as fast as possible. And obviously, checking everything slows us down. So, how do we solve this trade-off? When we pick verification and when we pick checking, there are two input ingredients to make this decision. One is how costly exactly is verification, because some verification can be very cheap. It's O1, or even you do O(n) work and your verification is just a constant time. So it's I don't even know how to describe it, because it's infinitely cheap. So for example, let's say that you are writing a for loop to iterate over array, and one verification you could do there is that you can check at the beginning of your loop that that the range over which you iterate is actually in bounds for the physical length of the array. And then you omit the checks in the body of the loop because, well, you only need to check this once at the beginning. And this is very cheap verification. Then there is verification. This is very cheap verification because the work we do is linear, so we do something for every element of the array, but the verification is actually constant because we only once check this bound. Then there is kind of a proportional verification. Let's say that's not a trivial for loop, but some kind of a while loop where the index changes in non-trivial way. Then we'll need to check the bounds on every access to the array. So here the work we do is linear, but also the extra verification work is also linear. We do extra check on every action we do. And then there is the case where the verification work might actually totally dominate the useful work we do. So for example, if you do a binary search and the binary search returns you a null, one possible verification there would be to go and do a linear search to confirm that there isn't actually a match. But that's kind of completely destroys performance, because binary search is logarithmic and linear search is linear. So your verification is actually algorithmically costlier than what you do. So that's kind of like one input, like what's like what is the cost of verification in terms of big O. The other input, is this a data plane or a control plane? It's kind of like data plane and control plane are like somewhat abstract notions, but basically the idea is that there are two kinds of things you do in software. In the data plane, you actually process data. So, for example, like let's say we have like a batch of 8,000 transfers. So the data plane is when we look at each one of those 8,000 transfers and do something with this. Control plane is about deciding what we need to do. So control plane is looking at this entire batch of 8,000 transfers and deciding whether it is the right time to start executing them because we replicated it to all the other machines, or whether we should wait for more acknowledgements from backups. And that is like kind of like abstract distinction. The concrete distinction between those two is that the amount of input to the data plane is linear, it's O(n). And the amount of inputs for the control plane is actually constant, is like O(1), or at least like much smaller than the data plane. So like control plane makes like a single decision, and then a lot of code runs over a lot of data in the data plane. So, and like in TrackAbittal, this distinction is embodied in this idea of batching. So a batch contains 8,000 transfer things. Everything which processes transfers themselves is a data plane. Everything that processes the entire batch as a whole, as one thing, is a control plane. And this is very long-winded answer to the question, but well, the question was really excellent, so sorry, not sorry about that. That gets us back to like this assertion. So, okay, if you are in a control plane, that means that you are running very little amount of code. Like performance of control plane doesn't matter because control plane is a very small fraction of the code. So if you are in control plane, then it is generally fine to, for example, spend a linear amount of time to verify constant amount of computation, because in control plane the n is small. In the data plane, this is generally prohibitive. In the data plane, you do want to limit yourself to assertions which do not slow down your computation too much. Okay. So, coming back to the FreeSet and to checkpoints, I don't think there is much we still need to discuss there. So let's take a pause here for a week, and in a week we'll come back here at 5 p.m. UTC live on Twitch, or failing that, we can always meet in a recording on our YouTube channel. And there, I think we will be discussing manifest log compaction. So we kind of like, you know, like we looked at the FreeSet, we looked at how we allocate block, we kind of like talked a little bit about the checkpoint. And when it comes to manifest log, we actually, like, you know, we will start using all this machinery we've been building so far for actually like writing some like real data to disk rather than like some metadata about what blocks are free and which blocks are released. Okay, so thanks again for joining, thanks for listening, thanks especially for asking questions, and see you in a week. Goodbye.